Let us recall what we have did in the previous lecture. In the previous lecture, we have talked about the sequence of functions f and x, where each fn's are real valued function defined or on a subset E of R. If this sequence of function at every point, this fn of x sequence of numbers is convergent, then we can say that this sequence of fn is converged pointwise. And if this sequence of numbers is converged to a function fx, then fx, it's called a limit of the sequence. The function f, it's called the limit of the function. And this way we can say that this fn is converged to pointwise to f. Under the pointwise convergence, we have observed certain things. If you go by a definition of epsilon definition, it says that for given epsilon greater than 0, there exists n0 belongs to n such that mode of fn of x minus fx is less than epsilon for every n greater than or equal to n0 and for every x belongs to E. Now this n0 which we got under the pointwise convergence, it may or may not depends on x that we have observed. So in the example, x raised to n is a sequence of function over the interval, closed interval 0 to 1. We have observed that this n0 is depends on x as well as epsilon. But in some of the examples, like x upon 1 upon n plus x, in this example we have observed that this n0 will not be depends on x, it only depends on epsilon. Also, very interesting observation we have make out is each fn's are continuous. Under the pointwise convergence, it does not mean that each f is this limit function f is continuous. Here, I am going to discuss regarding the differentiability and the integrability. That means each fn's are integrable, but it does not mean that the function f is integrable. And each fn's are differentiable, then it does not mean that the function f is differentiable. So for that, for difference, so for continuity, I already given the example. This x raised to n is the example because x raised to n in the interval 0 to 1, this will converge to the function 0 if x is your between 0 and 1, and if it is 1 if x is equal to 1. This is the each of x raised to n is the continuous functions, but its limit function, that is f, which is not continuous at x is equal to 0. So for continuity, we have already seen the example. Under the pointwise convergence, continuity is not preserved. That we have seen as an example. Here in this, we will discuss about under the pointwise convergence, the integrability is not differentiable. Means integrability is not preserved. Means that I have all fn's are Riemann integrable function. You probably know what is the definition of a Riemann integrable function. But its limit function will not be a Riemann integrable, may or may not be Riemann integrable. So I need to have certain examples. What is my claim is under the pointwise convergence, integrability or Riemann integrability is not preserved. So for that I need to construct an example in which each fn's are integrable but f is not integrable. Let us talk of that example here. So let us define this sequence sequence of functions, that is fn of x is equal to sorry, fm of x is equal to limit n tends to infinity cos m factorial pi x power 2n x belongs to R. So this is the function which depends on m. So you can just observe that is n is tending to infinity cos of m factorial pi x whole power x raised to n. Now I have to prove that this fn are integrable. Okay, and whatever the limit of this function, sequence of function, will not be integrable. Okay, so let us talk first of all this thing. We note that what is this value of mod of cos m factorial pi x, which is always less than or equal to 1 for every x belongs to R, that we know. Because cos function is always between -1 and 1. And if I take the power of this, or we have seen a result is this: if your x power n is there, will be tends to 0 if it is between this, and it is 0 if it is this is I have written 1, this should be 1 here. So if it is x is equal to 1, then it is 1. So this value of this function is between -1 and 1. And if I take the limit n tends to infinity, cos of m factorial pi x power 2n. Since it is a power 2n, if I write this modulus or I am not writing this modulus, is not make any difference because it is a power 2n is there. Now this will be having the two value. Either it will have a 0 value or it will have a 1 value. This will have a 0 value if it is the value is between 0 and 1, or -1 in between -1 and 1. It will have a 1 value if x is equal to 1. That means x power, that means this value, when it will achieve the value 1, then the answer will be 1. So it 1 if this will be 1. Okay, if cos m factorial pi x is equal to 1 and this is 0 otherwise. If it is not equal to 1, that means it has to be between -1 and 1. Okay, in that case, and it is a power 2n, so there is no problem with the -1 and 1. It's always between 0 and 1. It is always between 0 and 1 because it is power 2n. So this is always, otherwise it will be 0, and if it is equal to 1, then it is 1. Now when this value is equal to 1, when this value will be of the form 2 pi, first 0, 2 pi, 4 pi, or -2 pi, -4 pi, and so on. Then only then this value, cos of this value, so this quantity should be of this form. That means what is the restriction on x you have? M factorial pi is already there, so pi is there. Whenever this value of x is an integer, because m factorial is always contains a even number, so it is always having the even number m factorial more than 1. Okay, 2 factorial, 3 factorial. So if this x is an integer, If this x, because it is always, if it is -1, then also we don't have a problem because it is a power 2n is there. Understood? So it is, I can say this is equal to plus or -1. It is better to write it is plus or -1. So this is equal to, what I can write is 1 if this m factorial into x is an integer. Why? Because it is power 2n is there. I should have, it is a even integer, but it is power 2n, so there is minus sign will gone away now. So there is no, we can able to deal with the -1 due to this power 2n and 0 otherwise. So this function fn is this, fm of x is actually this function. This is the sequence 1 or -1. Now we have to see where this is. First question one can arise. First question can be arise that is this fm are integrable? What should be your answer? Is this fm are integrable? Why? If so, why it is integrable? So probably you have learned one result in the integrability. If any function have countably many discontinuity, then that function is integrable function. Riemann integrable. I'm talking about the Riemann integrable function. So this function is depends on m factorial into x. M factorial. If this is the quantity, it is integer, and it can be countable. So this function having the countably many discontinuity. So that's why this function fm is integrable. So we can note that here. We note that each fm are Riemann integrable. Now what will be the limit of this function? That means if I take limit m tends to infinity, what will happen to this limit? So for that I need to look at what is the value of x, because x belongs to R. So might be this x is a rational number or it is maybe an irrational number. So if x is irrational, if this x is irrational number, then this never m factorial into x is never be an integer. Okay. Therefore, what we can say is fm of x is always 0 for m belongs to. If it is irrational number. Now if f is rational, if x is rational, then your x is of the form p by q. When p is belongs to z and q is belongs to n, then this cos m factorial pi x whole power 2n, since this x is p of the form p by q, and if this m factorial, or I can say m, will be bigger than q, then this m factorial contains q. So in that condition, q will get cancelled. So this what is happen if your m is bigger than or equal to q, then this m factorial contains somewhere 1, 2 up to q, and then q plus 1 up to m. and into this pi x is there. So it is m factorial into pi x will cancel out with this q to this. So because it is pi into x, x is p by q and q will get cancelled out. And this is the integer into pi you will have. So in that case, this will have a 1 value because it is a cos into integer into pi. Power 2n is there. So it will have, so if m is greater than or equal to q, if your m is greater than or equal to q, then we'll have 1 value. And if I take a limit now, m tends to infinity, here cos m factorial pi x power 2n will be 1, because as per the definition, what is happened? There exists, as per the limit definition, there exists some n0. This is your n0. Q is the n0, such that m greater than or equal to n0, the value of this minus 1 will be less than or equal. So this is equal. So I can say the limit will be 1. If your x is belongs to q. So now we'll have these two things. The limit of this function is 0 if x is irrational, and it is 1 if it is rational. So finally what we can write is fm of x, a limit of m tends to infinity, is 0 if x is belongs to r minus q, and it is 1 if x is belongs to q. This is very well known function, and that I am giving you as a homework, or you already probably done in your analysis 2 class, that this function will not be a Riemann integrable function because it has uncountably many discontinuities that you can see, because it is discontinuity at every point of this function. This is the limit of the function. Okay. So therefore, this is your function f, which is a limit function. Here, the limit function is not Riemann integrable. So this conclude, what is conclude? Each fn's are integrable, but its limit function is not integrable. So what we conclude is, under the pointwise convergence, the integrability will not be preserved. Now let us discuss about the derivative. That means under the continuity, under the pointwise convergence, whether the differentiability will be preserved. So for that, let us consider this example. Let fn of x will be sin nx upon root n for every x belongs to R and for every n belongs to n. Now what you can observe for this example, I have to first prove that this sequence of function is convergent, and we can also show that the derivative and the limit cannot be interchangeable. That means if you have a limit of n tends to infinity, d by dx of fn of x, you cannot write this is equal to d by dx of limit of n tends to infinity fn of x. This we cannot, so this limit and the derivative you cannot interchange as per your convenience. Yeah, each fn's are differentiable and the limit is also differentiable. There is no problem with the differentiability, because we already talked that things, if each fn's are differentiable, a limit may not be differentiable, because it will not preserve the continuity. So we cannot talk about its differentiability also, because this is the example x power n, which converts to under the function or under the domain 0 to 1. This will converge to 0 if x is belongs to closed interval 0 to 1, open one, and 1 if x is equal to 1. So this function is not continuous, so there is no problem of the differentiability also. Each f, this x power n is differentiable, but the limit function is not differentiable. So we have already have an example of under the pointwise convergence, the differentiability is not preserved. But here there is something more is saying. It says that you cannot interchange this limit and the derivative sign as per your convenience. So this is the example, this is the counter example for that. So now let us consider this sin nx upon root n is less than or equal to 1 upon root n for every x belongs to R. This is, we can say, because sine function is always less than or equal to 1. And if I take the limit and by comparison test, if I take the limit n tends to infinity, a mode of n sin nx upon root n will be less than or equal to limit n tends to infinity 1 upon root n. And this will be 0, that we know. So therefore, the limit of this n tends to infinity sin nx upon root n is 0 for every x in R. This is there. And what is the limit function? Here the limit function is 0. We know that this each of these fn's are differentiable, and this f is also differentiable because it is a constant function. But let us talk about its derivative. So now, that is fn dash of x. The function is sin nx upon n, root n. The derivative of this function is n into cos nx upon root n. The derivative of sine function is cos, and the derivative of nx is n. So that's why this is root n into cos nx. And if I take the limit, therefore I am just talking about limit n tends to infinity d by dx of fn of x. So limit n tends to infinity a root of n into cos nx. This is less than or equal to 1, but into root n is n, which is unbounded. So this will converge to infinity. So this is equal to, this does not exist. So this is unbounded, but on the other side, that means and a d by dx of a limit of n tends to infinity fn of x. A limit of n tends to infinity fn of x, as per this, it is 0 that we can have. So this is d by dx of 0, and that is answer is 0. So these two quantities are not same. So hence what we can say here is limit n tends to infinity d by dx of fn of x will not equal to d by dx of limit n tends to infinity fn of x. So you cannot interchange this limit and the integration sign. Not only differentiability is not preserved, but if it is differentiable, then also you cannot interchange the limit and the integration sign in general. The next problem is like one can ask, if the differentiability is not interchanged with the limit, can the integration sign change with the limit? That also we cannot do in general. So for that I have another example. So let us define this fn of x, which is n square x 1 minus x square power n for every n in n and for every x which is in closed interval 0, 1. So your value of x is between closed interval 0, 1 and fn is this. What is our objective? We have to prove that this will not equal to this. That means the integration and the limit will not be interchangeable. The question is to what is the limit of this function? What is the limit of fn? So first we note that due to 1 minus x power square power n is there, and your x is between 0 and 1. So that is the first observation which we can make is, if your x is between 0 and 1, then x square is also between 0 and 1. So therefore 1 minus x, or I can say minus x square, is between minus 1 and 0. So therefore 0 less than 1 minus x square is less than 1. So 1 minus x square is between 0 and 1, and we know that power n, a limit of that one is always 0. Therefore limit of n tends to infinity, 1 minus x square raised to n is equal to 0. This is the first thing we can say. And what is the limit of this quantity? If your x is between 0 and 1, then only then. If it is also one should note that what is fn of 0. Now there is a point of at the end point 0 and 1, that is left. So if x is 0, then we know that this function is 0. And if fn of 1 is there, then this 1 minus x square, so x is 1, so this is also 0. So in fact I can say this value is, I should not write that, or we can say this. And therefore now a limit of n tends to infinity, n square x 1 minus x square power n will also be 0, because this quantity is tending to 0. If your x is, now I can write for in between 0 and any value between 0 and 1. So I can say that therefore fn of x is converged to pointwise to fx, where the function f is actually 0 function for every x belongs to closed interval 0. This we have. Now let us talk about that integration. What is the integration of fn of x dx? That is integration of this n square x 1 minus x square power n dx. What is the integration of this quantity? You can recall one of the formula which you have studied, that is fx raised to n into f dash of x dx will be fx raised to n plus 1 upon n plus 1 plus c. To get this result, you just take that fx is equal to t and substitute here. You will have this result. Now what is this function fx? Is this 1 minus x square is fx power n. Its derivative is minus 2x. So I have to adjust that quantity here. This is integration from 0 to 1. N square is constant, that I can take out. 1 minus x square power n into minus 2x. So I have multiply minus 2. I can divide my minus 2 here, dx. So the derivative of this function is here. So as per the argument, this is n square by minus 2, 1 minus x square raised to n plus 1 upon n plus 1, and the limit is from 0 to 1. If I put 1 here, this is 1 minus 1 will become 0, and when I put 0 here, that is 1 upon n plus 1. So this is finally n square upon n plus 1, 2 times, because this minus and this minus become plus. If I take the limit n tends to infinity, integration from 0 to 1 fn of x dx will be limit of n tends to infinity n square upon 2n plus 1. Since the numerator is increasing faster than the denominator, because it is an n square function and the denominator is a linear function, so obviously this will win, n square will win in the rest. Or if you don't understand in that manner, you just multiply and divide by n square. So this is n tends to infinity, this is n upon 2 into 1 plus 1 by n. So this will gives you infinity. So this side is infinity. What about the other side? That means now on the other side, integration is, we already have limit of n tends to infinity fn of x dx, integration of this quantity, integration from 0 to 1. A limit of the function which we already calculated, it is 0 function, which we have limit of this function is 0 function. So that's why this is 0 dx. So the answer is 0 on this side, and on the other side it is infinity. So therefore we can say that a limit n tends to infinity fn of x dx is not equal to a limit n tends to infinity integration from 0 to 1 fn of x dx. This will not be equal. That we can observe from this example. The questions are, and in this chapter we are going to discuss in which situation all these examples or all these conditions will fulfill. That means when we can interchange this limit and the integration, when we can interchange this differentiable and the limit, that means derivative sign and the limit sign, when each fn's are differentiable, the f is also differentiable. Under which situation each fn's are integrable, under which situation the f is integrable. Okay? All these questions are there, and we have to looking at these questions in this chapter. So to solution to this, we will define a new concept. It's called uniform convergence.